Let's continue with our example. Now, last time we talked about polling and samples. And so natural question that might come up is this. Let's suppose you do your polling correctly. Let's take Wisconsin, even though they screw up. Georgia's a better one. Let's take Georgia. Let's say you take Georgia, your poll, like your methods are all correct. You haven't screwed anything up. But what happens if it's still wrong anyways? Your poll can be wrong just by sheer random chance, especially if the state is very close. Biden won Georgia by 0.25%. When it's that close, it's very easy to call the state wrong. Now, you still might be plus or minus a point. If it's that close, you could still be wrong. But on the other hand, what if your poll says Trump is up by 4 or Biden's up by 4? You can get that just by random chance. And so a question that might naturally pop up is, can we find a way to figure out the chances of your sample not being representative just by sheer chance? And the answer is yes. And I'm going to use a bit of a weird example for this because this example isn't a poll, but as you probably sense the pattern by now, we use really easy examples just to explain the concepts. And then we go to the harder ones to actually work through them. So we're going to start with about the simplest one I can think of, and the one that 5 million other stats professors across the country use, coin flipping. Now here, this is what happens if we flip the coin once. Let's call this a sample size of 1. Flip the coin once. Don't worry about the colors of the bars. The red will go away pretty quick. Now, just for the sake of explaining the numbers, let's suppose if you get a heads, that's a 1, and a tails is a 0. So in this case, we flip a tails, we got a 1. Even though it's a sample size of 1, we can say our sample mean was 1. If we get a tails, we can say the sample mean is 0. Now, if a sample that small, you're going to have an extraordinarily wide standard deviation and variance, but we're just going with the bars. So this P, those are the odds that we get that sample mean. And this is a binomial distribution, nothing new yet. Not a single thing is new. This is really just starting off with a review of chapter 5. But now we're going to start changing things. What we're going to do is we're going to increase the sample size by 1. Come on, go. We increase sample size by 1. Basically we're flipping the coin twice. If we get heads twice, that's 2 1s, so we have 2. Our sample mean is 2. We get a heads and the tails, or tails and the heads, that's 1, so our sample mean is 1. And if we get 2 tails, we can call that 0. We have a 25% chance of being on the extremes, 50% in the middle. Now let's flip the coin 3 times. 3 times, we're probably going to have, so here, technically the X, that's the number of heads we get. I'm just saying, think of the number of heads as our sample mean. That's the only thing that's slightly different. And now what I'm going to do here, and the heights of these bars represent how often it'll happen. What I'm going to do here, we're going to keep going through this all the way up to 30. And I know those of you in Zoom can't really do it, but for those of you in person, so like here we have this really, looks like a trapezoid. The graph kind of looks like a trapezoid. As I go through, the shape's going to change. When you're very confident that you've seen the shape in this class before, I just want you to raise your hand. Don't say anything, but when you are very confident that you know what it looks like, just want you to raise your hand. We're going to go one at a time. 4, 5, 6, 7, 8, 9, and 10. Most of you should probably notice around 20. By the time we hit 30, I expect everyone to know. And don't be ashamed if you don't know, it's fine. 11, 12, 13, 14, 15, 16. Hands are starting to come up. 17, 18, 19, 20. This should be starting to look familiar. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. How many of you are reasonably sure that you've seen this shape before? That's nearly the entire class. I'll draw the little pump. For those of you who are over Zoom, it just looks like that. This is the normal distribution. Looks exactly like it. And if we keep increasing the sample size by past 30, it's not going to change. It's going to look like the hump. And the funny thing is, you're going to get this no matter what the odds of flipping the coin are. You can rig the coin. You can make it a 10% chance of getting heads. The shape's going to go to the left, but it's still going to be a normal distribution once we get to around 30. And this holds not just for, means. We can make this proportions. And I'll show you now. I'll switch to the, and don't worry, I'll post that PowerPoint in Zoom. Don't worry about these formulas. Just look at the shapes. Left-hand side happens with proportions. Right-hand side happens with means. Everywhere. If you take a ton of samples and they're of a sufficiently large size, and you just plot the distribution of all those sample means, it's going to look like a normal distribution. And since we know that, now that we know what it looks like, we can actually start figuring out the chances of getting a poll that's wrong. For example, this one on the left-hand side might be a terrible, terrible poll of California with a sample size of 30. That's pretty bad. If you have a sample size of 30 and you start polling California, you can see there's a decent chance you might have Trump winning it. Not because he is, not because your poll is like your methodology is wrong, it's because your sample size is that small. And we have a name for this. Oh, yes, I forgot to share screen. I apologize. Here we go. So those of y'all in Zoom, the left-hand one is, we see it happens with proportions. This bar is a bit high, and the reason why is because you see our buckets are a little bit wide. But the buckets are wide because the sample size wasn't all that big. But even then, with that small of a sample size, it's still relatively normal. We can see the one on the right is very normal. And there's a name for this. And now we'll get to the stuff where you can start writing down. And what I'm going to discuss here is going to be the focus of pretty much the entire remainder of this lecture, both definitions and applications of it. And we call this, I will zoom in for you, the central limit theorem. This is going to show up 5 million times on the assessment and on the WebWorks, whether directly or indirectly. So if we have any population and our sample size is sufficiently large, then the distribution of those sample means, we can approximate it with a normal distribution. Now, we'll discuss the properties of that distribution in a moment, but for now, we'll start with this. Now, you'll notice there's a condition there for the NP. Don't worry about that. Don't write that part down. You want to write out this part. The part right below it, I'll give you the shortcut momentarily. Now, the central limit theorem only applies when your sample size is sufficiently large. In the moving of the slides, what some might call a PowerPoint presentation, but I call it something stupider. Once we hit 30, it looked normal, and past that, it'll stay normal. For sample means, n equals 30 is the cutoff. If you're at 30 or higher than that, you can use a normal distribution. You want to write that down, it's going to show up. Pretty much every single word of this is going to show up in some way, shape, or form. So I'll give you just another moment to write that down. Don't worry about the rule of thumb. I'll discuss that in a moment. This is a very important one, so I just want to make sure I give you all time to get the whole thing. And for your cheat sheet, you're going to want to, if you want to, you can just take the whole whiteboard and put it on your cheat sheet because all of it's showing up, but especially this part. All right, still see a few people writing, give you a little bit more time to write it down. Okay. Now, that's the formal definition. Let's go, and here on the right-hand side, you'll notice this is out of the textbook, but it's a really good illustration, so I thought I would show it in class. We have three different populations and their distributions are all over the place. One of them is the uniform distribution. Second one is what could happen if two triangles try to have sex. And the right-hand one is flipping a terrible, terrible coin. Hey, it's true, you know it's true. And notice the higher and higher we increase our sample size, the more and more it looks like normal. Now you might say, hold on, that doesn't look like normal. That's normal, that's just really condensed. It's just really squished together. You can stretch it out and make it look normal. Normal is anything that looks like this. The only difference between these two is that one of them has a much wider standard deviation than the other one, but it's still normal. So now we have rules of thumb. One of them is for sample means. The other one is for sample proportions. Our first one, which is what I just said, if your sample size is 30 or higher, rule of thumb, that you can use the central limit theorem. Now, before you might ask, how can I use this? I'll show you how to use it in a moment. First of all, I should state what it is and what the conditions are. So the properties of this distribution, remember, this distribution is the distribution of all of our sample means, all of our possible sample means. The mean of the sample means will be the population mean. So for example, Georgia was basically 50-50. In that case, the mean or the mean of the proportions would be 50%. Now the standard deviation of it is equal to the population standard deviation divided by the square root of the sample size. In these examples and for the assessment, you'll be given the population standard deviation. But once we get into chapter 9 and onwards, we're going to stop assuming that we have it. But for now, we'll work with having it because it's easier to understand the concepts that way. So for example, let's say in Georgia, we didn't know this, but let's suppose just for the sake of argument, in Georgia, the standard deviation of the polls was 4%. And all these polls had a sample size of 100. Square root of 100 is 10. 4% over 10 would be 0.004, so 0.4%. So now we have another one, and this one's for proportions. Well, the one above was for sample size, but same concept. For proportions, I have written, you'll notice the inequality, I've written it as one big inequality, but it's not really big at all. It's rather nice and compact. It is an algebraic manipulation of the two above. I put it this way because it's easier for you to write down and work with. So let's suppose for these proportions, the population proportion is P, and the sample size of our poll or whatever is N. First thing you should do N times P. Do that, and then compare it with two things. It better be higher than 5, and it better be lower than the sample size minus 5. So for example, let's say that our sample size was 500. Then the sample size times the P better be higher than 5, and it better be lower than 495. The reason why I put it this way, because it's very, very easy to work with. You get your two boundaries immediately. One of them is just 5, and the other one is your sample size minus 5. Very easy to work with. And it also should be very easy to multiply your sample size by your population proportion. And if you satisfy those, then the mean of this distribution for the proportions will be the population proportion. The standard deviation is that square root of the P times 1 minus P divided by the square root of N in the bottom. So let me give an example. Let's do the correct example for, say, Georgia. The nice thing is all we need is a good guess for the state as a whole. So let's say for Georgia, we had 0.5, and that's our mu P bar, just 0.5, nothing more to it, just reading. This other one, and let's say we had a sample size of 100. So we have N equals 100 and P equals 0.5. Then our standard deviation will be the square root of 100. And then that 0.5 times 1 minus 0.5. So that would be square root of 0.25, which I believe is 1/2. And so then we get the same 0.4% as before. This is how with polls, you don't actually need the population standard deviation. All you need is a good guess for how the state as a whole might vote to get that poll standard deviation. And this is why the polls have very big sample sizes. What these polls are trying to do is minimize this standard deviation. we see in this case 0.4%, which means the odds of being more than, say, 2% below or 2% above the actual result is extremely small. And so that way, these pollsters, if they get a result that's just completely far removed from the actual result, they should know that wasn't by chance, that was by you screwing up. So that's how we know back in 2016, the polls were all disaster in Wisconsin because they were too far off for that to have happened by random chance, as we see with this very shorthand example. Now, don't worry, we'll get to some more complicated examples in a moment, but this is for the purpose of explaining concepts. So before I continue, are there any questions about these definitions? And don't worry, we'll work through some math examples in a moment. All right, we will move on. So back down to this. Now here, let me scroll up a little bit more. There we go. We'll start with the right-hand side. Another question that we might have is the population standard deviation. What happens if our population is not that big? If it is a rather small population, say our classroom, we only have 100 people, I think 118 right now total in the class. That's not all that big of a population. I mean, for a university class, that's pretty big, but in the grand scheme of things, that's not a lot. So the one on the left, and you're going to want to write all this down. We'll start with the one on the right, though. Well, the box is on the right. The standard deviation of our X bar, we have one of two things. We have the finite or infinite. The infinite, that's a bit misleading. I would personally categorize this as small population or sufficiently large population. When we're polling Georgia or polling Wisconsin, there's millions of people, and your poll is maybe 1,000 people. That is a sufficiently large population. On the other hand, if we're doing some sort of survey in the class, there's 118 of you. If even 50 of you respond, or even 25, these aren't really going to apply because they don't need to apply because the sample size is that big. Because, hypothetically speaking, if we could poll 500,000 people in Georgia, that'd be great. You don't even need, that's not a poll anymore. That's basically an election. I mean, if you don't believe me, the 2018 Georgia Secretary of State runoff, there were, I think, 700,000 voters. The runoffs don't have that many people. So if you could have a poll of 500,000 people, that's just basically an election at that point. But as a practical matter, there's not enough time in the day for that. So now the catch is the one on the left, it's a bit nasty. It's not pretty. The nice thing is we usually use the one on the right. And this one, this little box right here, this is the one you're primarily going to use. You want to have the one at the top for web work, but for this one down here, this is what's going to show up on the assessment and the reviews. So now, again, when I say infinite, I don't mean literally infinity. I mean basically sufficiently large. If your poll or your sample, yes. Yes. Yeah, you'll be able to use Desmos for the next two. For the assessment, you don't have to show any work because it's multiple choice. You get it or you don't. Just make sure for the midterm exam number 2, you show whatever you're putting into Desmos. You can use it, you just have to show what you're putting into it. But anyways, here's the general rule of thumb you use. Number 2, this one right here, this is the one that really matters. If your sample size is less than 5% of the population, then you can use the central limit theorem in conjunction with this standard deviation rule. And that's very nice and easy to compute. So technically, if I think Wisconsin had what, 2 million voters? Oh, it's probably more than that. 3 million? 3 million sounds right. In that case, 5% of that, that's well below 1 million, but that's well above 1,000. So technically, you could have a sample size of 1,000. Or 5,000, or 10,000, or 300. And all of those would satisfy this criterion. So the question you ask yourself is, okay, we know why we don't use small sample sizes, because then our results are going to be too wide. Because as you can see, the standard deviation of the sample means gets smaller the higher the sample size we have. Well, if that's the case, why don't we just make the sample bigger and bigger and bigger? The reason why is time and cost. I think 108 of you responded to the mid-semester evaluations. The remaining 10, I emailed them about 5 million times. If it takes 10 emails and they don't respond, another 10 emails probably isn't going to do anything. So it's the same concept with the polls. Getting a sample size of 1,000, that takes a few days because a lot of people just don't respond to the polls. Your phone blocks people that aren't like on your contacts list, or you shouldn't have a lot of people who can do the polls. Basically, the point is a poll of a sample size of 1,000 takes a few days to do. To do one of 10,000, not only do you not have the time, you probably don't have the money either. So although theoretically we'd like to make the sample size as big as we can, as a practical matter, there's a real world constraint. There's going to come a point when time and money block you from going higher. So generally speaking, the one on the right, so this one with this condition, they're going to be the ones that show up like 95% of the time. You might be asked a conceptual question about the one on the left, but generally speaking, the one on the right is one you're going to use in practice. Now, we have the same concept for p-bar. In this case, for p-bar, conditions applying the same way. N over n, 5% or less. The only thing that's different is the formulas. You can see we have the same population correction factor. We have the same square root of n minus n over n minus 1. And you'll notice that these two are the same thing and that these two are the same thing. We just have it's called a population correction factor. We don't need to go into terminology because it doesn't really matter. But again, what you're going to want to work with is this one and that condition. It applies in the same way. I know it's kind of a little bit boring, but we have to get all the definitions and formulas out of the way so we can actually start getting into some problems. Because this isn't like some of the previous ones where we can do part of the concepts and then do some problems, and then some more concepts, some more problems. For this one, it's kind of you get it all first, and then we start working through it. So I'll give you a moment to write it down, but while you're writing it down, is there anyone who has any questions about these concepts? Because this is the bulk of the concepts we've already had. And we're gonna start getting into the math afterwards. Yes. So for the p-bar, you use the one on the left if you have a finite population. Finite is the same definition as this. So, if your population size is 100 people, you got to use the one on the left no matter what, because your population is not all that big. But if your population is big enough, as long as your sample size doesn't get too unwieldy, you get to use the easy one. Generally speaking, just like with the one on the right, you're going to use the infinite population example 95% of the time. The one on the left, that's only going to come for conceptual questions. The assessment is going to be primarily concerned with the infinite population ones. Not necessarily because the populations are infinite, but because they're sufficiently large. I know it's a lot to write down. Is there anyone who needs more time to write stuff? All right. Let's move on to some examples. This one is off of web work. Many of y'all mentioned you prefer some web work problems for the whiteboards. That's what we're doing. I'm not going to do A and C because A and C have nothing to do with this chapter. That's just previous stuff. You might say, well, if it's previous stuff, why are we covering it? Because if you couldn't understand that coin flip example, you have no hope of understanding what's happening right now. But I'll just tell you, if you want to make life easy on yourself, part A, that's just a review of chapter 6. Part C is your answer from A to the power of 3 in this particular example. If it said all 4 have lengths that exceed 1/16, then B to the power of 4. Let's focus on part B though. That's what I want to discuss. So let's suppose this is kind of it's kind of a boring example. You're not going to see this show up much, but it's an easy example, which is what I want to start with. So we have this machine. We want to see if it's operating properly, because apparently when it was made in China, they made an oopsie daisy. Maybe they ate too many bats. Who knows? Anyways. So supposedly these subcomponents supposed to have a mean of 114 centimeters. Yes, these are meters, not inches, because the entire rest of the world does not use the imperial system. wake up sheeple. And we have a standard deviation of 5.4 centimeters. And so the question they're asking us is, let's say we pick 3 of them. What's the chance that their mean is 1/16? You cannot use chapter 6. You can't use chapter 5 because now we're dealing with a mean and our sample size is more than 1. Here's how we're going to approach it. So in this case, our sample size is 3. Okay? I don't know why you have to write that down. And here our mean length is 1/16. So we have our actually in this case we can say x bar is 1/16. We know our population mean is supposed to be 114. So we have mu is 114. The standard deviation of the population is 5.4. Standard deviation is 5.4. Now, with a lot of these, if you can't identify all of your numbers correctly, you're instantly going to get the answer wrong. And for the assessment, there's no partial credit. You get it or you don't. So just identifying this stuff first, you got to identify everything correctly, get the correct answer. That's why we do that first. So it's asking us what the chances that our mean length goes over 1/16. So I know many people are visual learners. Let's do a visual of what we have so far. Where'd my mouse go? Here's my mouse. Here is our distribution. That's not nice. Here we go. Here's the distribution of our sample means. And the mean of the distribution of our sample means is going to be 114. We're looking for 1/16. That's probably going to be maybe somewhere here. There we go. And we want to know what the chances are of falling over here. Well, we can use the properties of the normal distribution to figure this out. Here's the catch though. Our mean is still 114. Our standard deviation is not going to be 5.4. If you just take 5.4 and you run with it, you're going to get it wrong. The reason why is because we recall from up here, we have sigma, the population standard deviation, over the square root of our sample size. So if you don't divide by the square root of our sample size, you're instantly wrong. You're just wrong. So here, the standard deviation we're looking for, which you might call the standard deviation of our sample means, it is our sigma, which is 5.4, divided by the square root of our sample size, which is 3. So that's the square root of 3. And let me pull out a calculator. Square root of 3, 1 over that, times 5.4. Those of you at home, you don't have to worry about whether or not you can see it. In this case, this is equal to 3.11769, blah, 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 blah. Do not round anything until the end, especially for web work. If you're off by 0.001, it's going to mark it as wrong. You're going to have to see that you're wrong and then email me to ask me to fix it for you. So never round a single thing till the end. So now we know that the standard deviation of this is 3.11769, blah, 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 blah. Now we can use what we have from chapter 6 to solve this. So we need to get the z-score associated with 1/16. So our z-score is going to equal to 1/16 minus 114 divided by this. And to put that into a calculator, that'll be 0.6415. Oh, let's put that there. That's not good. There we go. This is equal to 0.6415. So now we have our z-score. We now need the probability of being above that z-score. So first we got to find the p-value associated with 0.6415. We use the table. You're going to want to have these tables next to you on the assessment. I recommend you print them out because if you print them out, you get to write on it. You get to write down more stuff. If you want, you can use the PDF file, but you don't get to write down as much. Also, if you're using the PDF file, that probably means you may not have prepared as much as you should have. So here, like before, we have the 0.6. And then we're looking for the 4. That's right here. We locate it. right here, 0.7389, that is wrong because we want above, this is below. Now we have to use the complement law. So we take 1 minus 0.7389. So 1 minus 0.7389, and that is equal to 0.261. Now we can round to 3 decimal places. That'll be our answer. So to put it in context, this 26.1% chance, that is the probability of if we take 3 components, that their mean length will be over 1/16. Now, I'll move to the right in a moment and give you a general process for how to solve these types of problems. But for now, I just figured I'd work through one and give you an application of what we're actually talking about. Some people are more conceptual, some are visual, some just like to see the numbers right in front of them. Are there any questions about what we've done so far? This is a very basic example. They're going to get a bit harder than this. Okay. Here I have another one. This one's a little bit trickier. I think there's an extra step. This one's applies very well for me. Not as much for y'all, but applies for me. Let's say I'm grading y'all's midterm exams, and it takes me 4.7 minutes to grade them with 2.3 per person. Some people, they're very easy to grade, either because they did very well or because they didn't show their work, in which case I just put -6 for everything and move on. Other people, their handwriting might be bad or they're getting a lot of partial credit, so maybe they'll be longer. So let's say we have 58 students, this class is bigger. Let's suppose we have 58. What are the odds he needs more than 5 hours? Now, if you're a student, maybe it'll take you 15 minutes to figure this out. But for stats professors, they can do it faster. This one is more so for me, but does a good job of explaining the concept. So let's start with our sample size. Our sample size is 58. And now I'm going to stop because right after this is where many people would screw up. They're going to say the mean is 4.7 and the standard deviation is 2.3. That is wrong. The reason why that's wrong is we're not grading one test, we're grading 58. So now to get our population mean, we have to multiply the mean for one person, which is 4.7, times the mean, or times our 58. And here you don't have to worry about any rounding, because it just comes out 4.7 times 58, 272.6. That is our mean. If you start with a mean of 4.7, you're instantly wrong. You can see, like with the formulas above, if you mark even one number as incorrect, you get the whole thing wrong. Maybe you'll get lucky and your answer won't match a single thing on the assessment. It won't come anywhere close to any of them. So that's an indicator for you that you should try again. And that's another reason why this one is an assessment. You get a bit of a checkpoint as whether or not you're correct, because if you get an answer and you're nowhere close to anything, you know you've gone off into la la land or something. Our standard deviation, the same thing applies. We got to multiply this 2.3 by our 58. Now, you might ask, why are we multiplying the 2.3 by 58? I can see multiplying it, why by 58? That's going to be a really wide standard deviation. Aren't the odds of being around 4.7 better than being 7 or 2.4? That is correct. But we multiply out the standard deviation, like with the normal distribution, we're more likely to get closer to the middle. Because for example, let's say we got 2 students, one of them, they aced it, the other one, a lot of partial credit. The one who aced it might only take me 3 minutes to grade them. The other one might take the full 7. But from the purposes of the sample mean, they cancel each other out. Because we have the -2 and the +2, bam, gone, 0. This is why it's okay to multiply this 2.3 by 58. Because even though we can theoretically get that far out, as a practical matter, we're going to be closer to the middle because oftentimes they'll cancel each other out. Anyways, multiply them together, and we have a standard deviation of 133.4. And now we are asking for 5 hours And unless you failed second grade math, 5 hours is 300 minutes. Now, if we, like before, if we take this sigma, so we'll do the visual again, for those that like, for those that like the visuals. Here we go, is our standard deviation. The mean is 272.6. And we want to see what the odds are it takes more than 300. Now, as a note, if I said less than 300, you have one less step because you don't have to use the complement law. So as you recall, the z-tables, it's the probability to the left. The reason why I'm taking this stuff to the right is because that's what was on web work, and that's what costed people lots of points on the previous midterm exam. Lots of people forgot complement laws at some point. Now, again, we can't use this standard deviation of 133.4, and the reason why is because that's too big. We'll use our formula from before, the population standard deviation of sigma over the square root of n. So in this case, the true sigma we want, so we'll call, remember this is sigma x bar. This is 133.4. And we divide this by the square root of our sample size. In this case, that's 58. This is another reason why it was okay for us to multiply that standard deviation by 58. That's another reason why it was okay, because we're dividing by the square root of 58 anyways. If you want to think about it, what we've done is we multiplied the original standard deviation by 58 and then divided by the square root of 58. So if you want, you can say multiplying that by the square root of 58, but that's more of an algebraic thing. And here we have square root of 58, 1 over that times 133.4. This is 17.516 to 7, blah, 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 blah. Never round until the end. Do not round a single thing till the end. Now we have our standard deviation. Now we can compute our z-score. So our z-score is what we're looking at, which is 300, 5 hours, minus our sample mean, or the population of the sample means, 272.6, and we divide it by this. And now 300 minus 272.6 divided by 17.51627. I think there was an 8 after that, but good enough. And that's a z-score of 1.5642, blah, 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 blah. These numbers just come out of a calculator. So if those of you at home who can't see the calculator, that's fine. You just put it into a calculator. Once you have your z-score, you can actually stop after the second decimal place, after you've rounded, of course, because our z-table only goes 2 decimal places. And I've made sure on the assessment, it goes through like we're working the z-scores from this table, same as with the practice assessment. So on web work, it'll take that exact decimal z-score and put it in, but when you round to 3, you'll get the same answer. So at this point, if you want to round the z-score, you can, because you're basically at the end right now. Regardless, we have a z-score 1.56. We start with our 1.5. Now we need the 0.06, which is right here. Go down. That is our probability. Remember, that's being to the left of it. We got to go to the right. So we have to use the complement law. So we have 1 minus 0.9406. Which we round that to 3 decimal places, we can say is 0.059. And in my case, those are the chances of, if there were 58 of you, it taking me longer than 5 hours to grade, roughly 6%. The extra step we had here was we had to convert our mean and standard deviation for just one test up to the sample. But the process would be the same across all examples. You just multiply the mean for one by how many you have. Same for the standard deviation. When you calculate the standard deviation of the sample means, you correct for that with the square root. We have a few questions. So the complement law. The reason why we take the complement law, you'll notice we need more than 5 hours. If you recall, and this will show up on your Z tables, you recall your Z tables, you have some sort of value here, and it wants it to the left. That's what these are. But this one here, it's not asking us to the left. It says more than 5, so we want to the right. Since this number from the Z table gives us the probability of being to the left, we take the complement of that to get the probability of being to the right, because to the right is above. That answer y'all's questions over Zoom? Chris and Jordan? Yes, Brayden, that's correct. We have roughly a 6% chance of taking more than 5 hours. On the assessment, you'd say 5.9% chance, because that's the 3 decimal places. You had a question? It's the same one? Okay. Now, the nice thing is, if I said below 5 hours, you don't have to use the complement law. You get to go straight to the answer. What number, Chloe? Oh, the answer to the last step is 0.59. That's correct. 0.059. There we go. Jordan, the way we got the 6%, we take the 1 minus the complement. Where'd the 0.94 come from? That was the probability associated with our Z-score. Here's what we multiply by 58. Because in our example, to mark a single test, it's 4.7. We're not asking about a single person. We're asking about 58 people. That's why we have to multiply by 58, because we got 58 people and not 1. That makes sense? Everyone in person is intensely watching you to see when you say yes. Anyways, I don't think the difficulty in terms of the web work or the assessments get too much more difficult than this for this type of problem. So now let's move on. Now this one, I'm going to let you work on it. The only thing that changes here, you remember, you saw this in the last lecture. It's just this time you're actually working through the whole problem now. In the last lecture, you identified the numbers. With this one, the process is nearly the exact same. The only 2 things that change, number 1, we're doing proportions now. So you have the slightly different formula. And number 2, keep in mind, oh, come on, where'd my mouse go? Keep in mind now it's less than, which means this time around you don't have to use the complement law. So 1 less step. In the last one, there were 58 tests. Yes, exactly. We had only 1 test, and 1 test, I believe, was 4.7 minutes. We wanted 58 tests. You got to multiply to scale it up. But it's pretty straightforward. If they give you the sample mean or standard deviation for just one thing, and your sample size is more than 1, you just multiply by your sample size and you're good to go. I won't do anything fancy like the sample mean for 5 people is 5 minutes. What about 25? No, you'll either get the population of all 58 people, their mean, or the mean for 1. The reason why we didn't multiply it by 3 in the first example was because in the first example, notice that in this case, we're talking about the mean length going over 116, because we're asking for the mean length. Whereas in the previous one, we're dealing with the probability. I know that might seem a little bit confusing. Think of it this way. The mean length of 1 subcomponent is 114. If I asked you the total length of 3 subcomponents, then we'd multiply by 3. But I'm not. I'm asking you for the mean of the 3. If that problem we just had, if I asked you what's the mean time to grade 1 student, you'd still say 4.7. Yes. But case in point, we don't multiply by 3 here because it's not asking us for the total length of all 3. Whereas in this one, it's asking for the total length of all 58. Which numbers? Should be up to 9. Which numbers are you referring to? Here, let's complement law. That's just the z-score. That should be the rest of the labels for that one. And then this one right here, this is complement law. The rest of it's already labeled. As you go here, this is the calculation for the sample mean, standard deviation. This is our z-score. So everything else is labeled. Oh, well, this one you're supposed to figure it out. So I'll give you about a minute. Again, the first thing you need to do, identify your values. In about a minute, we'll go over those values. And then after that, you'll work through the remainder of it. Actually, I'm pretty sure most of you have already probably started doing that one. So for this one, the population P, notice technically what I'm showing you right here, we did this last time. But as a refresher, our P is 52.7%. The standard deviation, you don't know, you calculate that. In this case, we have N is equal to 480. Those are the only two labels you need. With the proportions, it's less likely you identify something wrong because there's only two things you need. All you need is the P and the N, and that's pretty much it. So now I'll give you about a minute to work through it. I have the Z table here. So you can use this Z table to find your value. Spoiler alert, it's one of these Z values. So if you have a positive Z value, you've screwed up somewhere. Also, the lecture videos to those on Zoom who asked, it should be uploaded no later than an hour after class ending. What I do is I stay after so it can convert, and then I trim off the useless talk at the beginning and the end, like, you know, just the housekeeping, and then I just upload that. Yes. Correct, because our z-scores, let me draw this so you have it next to you. Our z-scores, you're going to be somewhere down here. I'm not going to tell you exactly where, but you're going to be down here. Any z-score gives you the probability of being to the left. If I asked you greater than 49.9, then you'd have to use the complement law because the tables always give you to the left. So nice shorthand, if it says less than or below, you don't have to use complement law. If it says greater than or above, you're going to have to use it. All right, does anyone need more time? All right. So we know that the mean of our P bar is just the P. So that's 0.527. That's just this. That's a nice easy step. The other one, we need the standard deviation of the P bar, which as you can see over here, you can use that or this one. They're both the same thing. So we have the square root of the P times 1 minus P over N. So if we go back over here, this is equal to the square root. And notice you can put the square root into both the numerator and denominator. That's just an algebra rule. That's what I'm going to go with. So we have 0.527 times 1 minus 0.527 divided by the square root of our sample size, 480. Now I'm going to switch to Desmos because I'm pretty sure many of you will use Desmos to do the math for you. Luckily for many of you, this time there's no work to show. You just do it. It's multiple choice. I must stress, keep in mind, on the midterm exam number 2, anything you put into Desmos, you have to tell me what you're putting into it. You can't just go straight to the answer and show no work. So let's go ahead and switch over to that. I will, out of the way. There we go. Let me switch over here. All right, let me share for those of y'all over Zoom. So our population standard deviation, and for those who don't know, you just type in SQRT to get square root of Desmos, save you a bit of time. So we have 0.527 times 1 minus 0.527. And then we had the square root of 480 in the denominator. So that is standard deviation of our P bars. Notice that example is pretty nicely in line with the one I gave y'all for Georgia earlier. It's also called the margin of error, which we already discussed. So here, 0.002788. Let's go write that down. Switch back over to the whiteboard. So therefore, we know this is 0.227. I think it was 0.22788. Oh, sorry, I forgot the 0. There we go, 0.022788. Sorry about that. Yeah. All right. Now we have that. Now we compute our z-score. Let me scroll up a little bit. So our z-score here, we're looking for below 49.9. So we have 0.499 minus the population mean proportion, which is 0.527 divided by this. And I will switch back to Desmos now. I'll type it in there for those of you over Zoom. If you want to save yourself some time, you can say this is S. And then therefore our z-score Z is going to be equal to the 0.499 minus the 0.527 divided by our S. By doing this, you never have to worry about the rounding. So here, now we can round the z-score to our second decimal place because that's what the table has. So in this case, the z-score is negative 1.23. Let's go back to the whiteboard. Here's the whiteboard. Here we go. Which is negative 1.23. Now we use the table. There's the negative 1.2. There's the 0.03. Bring it down. That number is our answer. So our answer is 0.109. You don't have to use complement law because we went in below that. Now, you might ask, why 49.9? That is very arbitrary. Because if you have 49.9, you lose. If you have 48, you lose. So you can think about that, how a lot of these campaigns approach it. That's why the Clinton campaign, they were so confident they were going to win. Because in order for them to have lost, all the polls had to be wrong. And they were assuming the polls were being correctly done. And if the polls were correctly done, then the Clinton campaign would have been right. But the polls were all systematically off. That's how most people were so dead wrong about 2016. Are there any questions about this example? Now, let's suppose we were instead interested in a close election. So for example, close might be between 49 and 51. In this case, maybe that might be here and here. The probability is right here. So 10.9%. Let's suppose I asked you, or we'll just stick with one dotted line. Let's stick with this one. What if I asked you, what are the chances of being in between these two dotted lines. 90% of the process is the exact same. You still identify your P, you still identify your N, still the mu P bar, still the same sigma. There are only two extra steps. Extra step number one, well, you could say three, but one of them's a substep of the other one. You would have to get the Z value associated with that, then the P value with that, and then you'd subtract the smaller P value from the big one. But that's just a repeat of chapter 6. Now, before we go on to some more examples, I'm going to give you a little bit of a workflow for how to solve these problems. Right down here. So we'll start with the top one, because this top one, this is what you've been doing. First thing you want to do, and you can say X, like it could be P value, doesn't matter. I just pick X. So the mean of our sample means, or sample proportion, doesn't matter. That is the population mean or population proportion. Basically, step one is a reading step. Can you read the problem? If you can't, you got to go back to 3rd grade English. And then for the formulas, we'll use one or the other. For the case, the first two problems, it was the population standard deviation divided by the square root of n. For the one we just did, it was the square root of the p times the 1 minus p. And you divide that by the square root of n. And that will give you the standard deviation of your sample means. Get the z-score with that, use your table. If you're below, like the one you just did, you're done. If it was the first two that we did, you have to take the complement of it because it's asking for above. And like I just said, if you want to get in between, you do the above for both of them. Exact same, and your last step, subtract the smaller from the bigger. So now you have this one. Don't worry about the working backwards. We'll do working backwards in a moment. I'm going to give you an example where you have to find in between, and I want you to use this exact process to do that. You can use this process for everything. It will always work if you get your initial numbers correct. So I'll give you one right here. Where is it? Right here. Oh, it's right here. Where's the in between? Oh, those are the backward ones. That's fine. With this one, we'll just add one extra step. So let's copy paste this over to the right and do one extra step. Whoop. There we go. This is the advantage of using a computer, not an actual in-person whiteboard. Something that we're going to leave a lot of this work, but what I want you to do differently this time is I want you to find the chance of being in between, come on, bigger, 49.9% and 51.1%. Notice for 49.9, same probability as before. So all I'm asking you to do, find the probability for 51.1, then subtract the smaller from the bigger. I'll give you a minute to do it. Half of the work is already, actually most of the work is already done for you. So I'll give you a minute to do this extra one. And here, let me get rid of that. Oh, less, sorry, less. There you go. I'll give you about a minute or two to work on this one. As a little bit of a hint, in the little cheat sheet I gave you, you get to skip the first couple of steps because you've already done them. This doesn't look pretty. That's making it worse. There we go. Does anyone need more time? Okay, with this one, we just have pretty much two extra steps. The first step, we need another z-score. So now here we have 51.1%, so 0.511 minus 0.527 divided by that same standard deviation. And now in this case, I'll just put it in the Desmo, save some time. Don't worry at home if you can't see it. I have one negative 0.7. So negative 0.70. Technically, it's not in this table, but it was in the earlier ones, I believe. Somewhere down here. That wasn't. That's fine. I will pull it up then. Give me a moment. It's fine. I'll share it for y'all in Zoom so y'all can see. That's positive. I want negative. There we go. Good enough. Let me switch in Zoom so y'all can see it. Here we go. So we had negative 0.7. That's just negative 0.70. So 0.24196. So there we go. That's just this right there. Let me switch back over. Here we go. And then this p-value was 0.24196. We just subtract the smaller from the bigger. So 0.24196 minus the 0.1093. So this, so 0.24196 minus the 1093. I'll label this as well. Those of you who want the labeling. And that is 0.133. So the probability of getting a polling average that's basically a really close selection, in this case was about 13.3%. Are there any questions about finding any probabilities for sample means, whether it's below or above or in between? Well, we can work backwards. Let's work backwards and then we're done. And so here I'm going to do one example working backwards and the other one then you'll do yourself. So now this one is actually off of one of the extra homeworks, mostly because WebWork didn't have a lot of this. This will be on the assessment though, which is why I'm showing you it. So this one is unnecessarily boring. You know I didn't write it because it'd be probably goofier if I did. So let's suppose these apples, we have our mean is 7. And again, we don't have to multiply by 30. And the reason why is because they want the average weight. So the average weight's still 7. So we know our mu is 7 and our sigma is 2 and is 30. It's a box of 30. And I'll emphasize we don't multiply by 30 because it says average weight, not total weight. If it said total weight, then we'd multiply by 30. Now this time it's asking us below what value do 12.1 fall below. And for this one, we're going to do what we did before, but now we're going backwards. So when we work backwards, the first thing we got to do is find the z-score. Here's how we find the z-score. This number, 12.1, so 0.121, find that in the table. In this case, 0.121. Where is it? There we go. 0.121 is right there. So this is right there. And now we need to find the z-score for that. And that we have the negative 1.1 and the 0.07. So our z-score is negative 1.17. You'll notice the process compared to chapter 6 has not changed. We start off the exact same way. Okay, so that's our z-score. Now this is where the process changes because this standard deviation of 2 is incorrect. We don't want that standard deviation because we now have a box of 30. So using our formula, the standard deviation of our weights is our 2, which is this, over the square root of 30. which if we put that into the calculator, is about 0.365148, blah, 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 blah. So 0.36514, blah, 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 blah. Now we can use the z-score formula. So negative 1.17 is equal to the value we're looking for. We'll call that weight minus 7 divided by this. So we multiply that number we got by the negative 1.17. This thing doesn't let me put it at, so let's go to Desmos. That makes it easier. I won't share this with those of you at home because this is just throwing it into a calculator. So negative 1.17 times 2 over the square root of 30, because we multiply out by the standard deviation. And then we add 7. Those of you at home, you just throw it into a calculator. That's just what I did right here. I can snip it, make it easier for y'all. At home, this is what I did. Or well, for those of you at home, this is what I did. There you go. It's just solving, we multiply out by that standard deviation. Then we add 7. So our weight is 6.573 ounces. So we work backwards. Like the only thing that changes here compared to chapter 6 is now we have to get a new standard deviation. The rest of the process is the same. So this negative 1.17, we want the value that 12.1% fall below. Since we have a box of 30, remember the 30 rule, sample size is large enough. So we can use our normal distribution by the central limit theorem. So we need to find the z-score that 12.1% of data values fall below. We found that by looking for 0.121 in the table right here. This 0.121 was negative 1.1 and 0.07, so negative 1.17. From there, it's pretty elementary. Compared to chapter 6, again, the only extra step is you have to get the correct standard deviation. Now, I'm gonna have you do a practice one, but now let's go back to this, working backwards. If I say below what value, do the above quite literally backwards. You're fine, don't worry. You just find the probability of the z-score, and then you go 1, 2, 3. If it says above that, you have to get the complement of that. Because for example, if I said above what value, like for example, 12.1%, above what value do 12.1% reside? You would then have to convert that 12.1 to 0.879 and then find that value. So if it says above, you use the complement law. Other than that, once you do that, you see the process finishes off the exact same. The nice thing is when you're working backwards, funnily enough, working backwards in this case is a bit easier than working forwards. It's kind of like when we did that margin of error example in the previous lecture. So now that you have this, I'll give you one to do on your own. And that will be our last example. And then we will be done with chapter 7 and out on time. So here's the last one. You'll notice because it says below, you don't have to use the complement law. So I will give you about a minute or two to work on this. All right, does anyone need more time? All right. We need to find 0.834 in the table. That is right here. Draw the arrows up and to the left. Our z-score is 0.97. Now, to save us some time, all the rest of the numbers are the same. Our p, our sigma, the mu, the sigma, and the n, and this sigma x are all the same. So I will save us some time and just copy this over. Same thing. See, the rest of the problem is the same. All I did was just change the number. Now we use our z-score formula. 0.97 is equal to the weight we're looking for, W, minus 7 divided by this. And if I go back to here, I will snip this for those of you at home so you can see it. There we go. And then I will paste it right here, just because I saved us some time. And this is our answer. The only thing that changed was one number. That was it. You can see working back is pretty easy. Now, before I continue on the very last conceptual part, which should take no longer than 1 minute, any questions about working backwards? Yes. So we are looking for the value that, for those of you on Zoom, the question was, we're not sure where this z-score is coming from. So we're trying, first of all, we're looking for the z-score that corresponds to 83.4% being below. You follow? Yeah. And so we're looking for 83.4% below. Another key indicator, normally distributed, and box of 30, central limit theorem. For pretty much all the problems, it's implied you can use central limit. And I have designed them all in such a way that if it asks you for the finite population, that's on WebWork. For the assessment, it's all going to be the easier formulas, because not only are they easier, they're the ones that actually pop up. And so we just look for the 0.834, and that corresponds to 0.9 and 0.07, so 0.97. On the exam, if you're asked to work backwards, I will give you probabilities that directly correspond to one in the table. So for example, I won't give you 0.8341 because that's technically not there. All you could do was guess that it was between 0.97 and 0.98. I will give you exact values that correspond to this table. One last conceptual part. There's one problem I'm not going to ask you to do, and that might be something along the lines of this. Between what two weights do 68% of the values fall in between? Now, for empirical rule, you're instantly going to say plus or minus 1. For this, there are infinite solutions. Here's why. Here's our graph. The one from the empirical rule might say it's in between these two. On the other hand, it could be in between these two. Or it could be, oh, what did I just do? There we go. Or it could be in between these two. You will not be asked to work backwards from two values, say in between two values, because there's an infinite number of solutions. The only backwards you'll have to do for this particular lecture is just from one p-value below or above. Other than that, that is it. We have finished on time. I expect we'll finish on time or early next time as well. Other than that, enjoy the rest of your evening.